All right, so now that we know a little bit about how to take derivatives, at least of some functions, I want to talk a little bit about a derivative that we actually already know about. And it's going to help us make some connections with why we care about derivatives and where we're going to use them. So the beginning of our course, we talked about finding average velocity. And that was the difference in, like, your change in position divided by the change in time. Well, to find that average velocity, we had to be thinking about the distance and thinking about how the distance changed. So we actually started with a graph of distance as a function of time. And we found out that what we were really doing, we were letting 2 points get closer and closer, and we were finding the slope in between them. And then we found out that if we did it right, we could even find the slope at a single point without having a second point to use. And we called that slope the derivative. So now that we go back and think about it, what we were finding, we found average velocity and then let the 2 times get closer and closer, and we found instantaneous velocity. We were finding out that velocity is the derivative of position. And if we think of derivatives, we've talked about a lot of ways to think about derivatives. 2 big ones are slope and rate of change. So rate of change meaning a description of how one quantity is changing with respect to another. And so if you think about that, if you talk about how somebody's distance is changing, well, it changes based on how fast they're going. So a description of how distance changes is a description of velocity. So velocity is the rate of change of distance. Velocity is the derivative of distance. So, ladies and gentlemen, the top of your 3.4 notes, big important idea. Velocity is the first derivative of position. If you want to use that prime notation, if s is our position function, then v of t, velocity, is s prime of t. Or we can say it's the derivative of s with respect to t. That's the other notation for it, right? So the prime notation or this ds dt notation both mean first derivative of position is velocity. So we have to be really careful not to get confused between velocity and speed and distance, because sort of inconveniently, historically, conventionally, we use s to stand for position. Some people say CS in a context where we've been talking about velocity, and they think automatically they think speed. S does not stand for speed. S is position. There's other notations we use for position too, but typically S is position. Velocity is the derivative of position. And then it turns out speed is a very special kind of function. Specifically, and you do have to know this, speed is the absolute value of velocity. And notice this, we don't even usually give it a letter. I think because we don't want to confuse it with S standing for position. And another reason, we don't need another letter because speed is defined specifically based on the velocity function. It's specifically the absolute value of the velocity function. So there's a place for this in your notes. All right, so the first side of this paper is all about velocity and speed. So important velocity fact number 1. There isn't a spot for it on your important facts paper. You definitely have to know it. A particle or something that moves, a body, is at rest if its velocity is 0. And look at this. I hope you saw this and were like, oh, I feel like writing an equation. Velocity equals 0. This is a released multiple choice question from 1988. We have a particle moving along the x-axis. So let's talk about this. The x-axis is horizontal, which means that I can describe something's position on the x-axis just by giving the x-coordinate, because the y-coordinate everywhere is 0. So that's why here I'm using this notation x of t, because where this thing, particle, it's just a physics name for something, something that has space, but not that much space that it takes up. Something is moving along the x-axis. So it might move and then move faster, or it might move back and forward. but it's moving along the x-axis, so its position I can give with an x value. That's why I've decided to call the function x of t, because the output is an x value. So I have a particle that's moving along the x-axis with this, so it has this position, t cubed minus 3t squared minus 9t plus 1. And I've been asked for what value or values of t is the particle at rest. So I hope you were already thinking about doing it, especially because I already accidentally almost gave it away. I'm going to find the velocity function and set it equal to 0. Well, I don't have a velocity function. I've been given the position function. That's where the calculus comes in, because you know now that to find velocity, we're going to take the derivative of position. So I have labeled my velocity function v of t. I've used the sum and difference rule and also the power rule to find v of t. So this 3 comes down to the front to multiply, this 2 comes to the front to multiply the 3, and I end up with v of t is equal to 3t squared minus 6t minus 9. I decided that my particle is going to be at rest when the velocity equals 0. So that's why I've written this equation here, 0 equals 3t squared minus 6t minus 9. Now I notice the degree of that equation is 2, and I solve degree 2 and higher equations using the zero product property. That means I want to factor and cancel. So here I've factored out the common factor of 3. Now I notice I have this polynomial, trinomial, t squared minus 2t minus 3. I need to think of two numbers that multiply to negative 3 and add up to negative 2. So now I factored as that 3 factor comes out to the front, t minus 3 times t plus 1. I'm going to think of all the t values that would make this statement true, that would make this right-hand side of the equation equal to 0. Well, that's going to happen when t minus 3 equals 0, which happens at t equals 3, or when t plus 1 equals 0, which happens at t equals negative 1. Well, in this problem, t stood for time, and we were told our function, our original position function, x of t, was only defined for positive, well, non-negative t values. I'm going to throw out this negative 1 time value and report that my particle is at rest at time t equals 3, because the velocity at time 3 is 0, and a particle is at rest when its velocity is 0. All right, so important velocity fact number 2, when velocity is positive, motion is forward. But you have to look at the context to understand what forward means in the context. You have a particle moving along the x-axis, forward is to the right, where the x values get bigger. If you have a particle that's moving along the y-axis, so up and down, then we have when velocity is positive, then motion is upward. If you leave your house in the morning and your velocity is positive, you're going toward school. And if you leave school in the afternoon and you're going toward your home, then your velocity is positive, because you're going wherever whatever forward means. When you're at school, you want to get home. When you're at home, you want to get to school. Similarly, when velocity is negative, the motion is backward, whatever backward means in the context. And here's the one that's for sure going to show up on the test. Direction changes. That means you change from going forward to backward or backward to forward when velocity changes sign. And specifically, that means changing from positive to negative or from negative to positive. So let's take a look at this picture down here. Okay, so I have a particle moving along the x-axis, and here's its velocity. At what time or times does the particle change direction? Well, I notice that here, I'll use red for negative. The velocity is negative. In this section, the velocity is negative. In this section, the velocity is positive. I'm saying this because the velocity, that part of the